In this presentation, we're going to discuss about binary numbers and operations. So what are binary numbers? The numbers we use in our daily life are 10 base numerals. For example, the number 348 is equal to 3 into 100, which is 10 raised to 2, plus 4 into 10 raised to 1 plus 8. While we humans use 10 base numerals, computers use 2 base numeral for its calculations. So 2 base numeral contains only ones and zeros. So now we're going to see a demo of 10 base numerals and 2 base numerals in calc.exe. In the start run, type calc.exe. So you will get calculator. So inside the calculator, in the view, we have to select programmer. We should see something like this. In this, we have a couple of different options up here. In that, select decimals. Here you can select byte for the time being. Now, if you type a number 125, and if I click on bin, we'll get the equivalent binary number. 1111 is the binary equivalent of 125. So like that, every decimal number has a binary equivalent. So now I'm going to type a binary number 11011 and convert it into decimal. So I got 115. So when we select binary, if you look at this, all the other options other than 0 and 1 is disabled. For example, I cannot press 7 or 8 or 9, but only 0 and 1 in the calculator. So the bottom line is every number has a binary number equivalent, and computer uses binary numbers instead of decimals. Now let's go back to our slides. So we have seen this demo. So following are some of the mappings between binary numbers and 10 base numerals, which is decimals. If you carefully observe, you can see a pattern up there. So some of the jargons. One digit of a 2 base numeral is called a bit. 8 bits give a byte. 2 bytes or 16 bits give a word. 4 bytes or 32-bit give a D word or double word. So following are some of the facts which is worth remembering when we deal with binary numbers. Any number can be expressed in 2 base numeral, as we mentioned. A 2 base number of n digits can hold a number which has maximum value of 2 raised to n minus 1. So 2 to the power n minus 1. So for example, an 8-bit 2 base numeral or an 8-bit number can hold up to 2 raised to 8 minus 1 different integers. Everything you see or deal with a computer, programs, video, music, Facebook page, you name it, all are ones and zeros. Basically they are either a 2 base number or a collection of 2 base number. So what makes a difference is the way programs interpret them. In case of a Facebook page, which is nothing but a big binary number, is interpreted by your browser as a web page and displayed as a web page. That same binary number can be interpreted by some other program as something else. So let's see a couple of operations related to binary numbers. We do operations like addition, subtraction, division, etc. with 10 base numerals in a daily basis. So we call it arithmetic. 2 base numerals also has those operations. Along with that, 2 base numeral has some additional operations as well. So AND, NOT, OR, NOR, XOR, left shift, right shift, etc. are 2 base numeral operations. So first, AND operation. The first column is the first input and second column is the second input and third column is the output. So remember that in the AND operation, only if both the inputs are 1, we will get 1 output. All other case, the output is 0. So this is OR operation. So in the case of OR operations, we get 0 only if both the operands are 0. in the case of an XOR, we get a 1 as output if the inputs are different. So the inputs are same, we get a 0. NOT or complement, we have only one operand in this case. So whatever operand, we will get the opposite as the output. 0, 1, 1, 0. So these are the shift operations. So we shift the bits one by one. So if you look carefully, you will understand it, which is pretty self-explanatory. So the first one is left shift. So we are shifting the 1 to the left. So it was in the beginning, then the second position, third position, and it is in the last position. Like that, right shift. So now let's see a C program which does all the operations we have seen so far. So following is a simple program which does most of the operations we have seen. So we have two integers a and b, and we have bitwise AND operation here, and we are assigning it to Z. We have bitwise OR operator here, and we are assigning the result to D. We have the complement operator here, and we are assigning to E. So int is a 32-bit signed number, so we have to take care of that. So this is the shifting operator. So this is the right shift, this is the left shift. Before we start executing, we have to see what is the binary equivalent of 10. So we have 10 here. The binary equivalent of 10 is 1010. So I'm going to note that down in a notepad just for easy reference. Control C, Control V, equal to 10. Now let us see what is the equivalent of 20. So I'm going to type 20 here. So this is the equivalent of 20. Control A, Control C, Control V, equal to 20. So we got the equivalents. So now we know what is in our A and B in binary. Now let's try to manually calculate the output of A ampersand B. So I have A ampersand B. So I'm assuming a 0 here. So as we have seen, AND will become 1 only if both the inputs are 1. So 0, 1, which is 0, 1, 0, which is 0, 0, 0, 0. So if we do AND operation between 10 and 20, the result is 0. So 0 binary is 0 decimal. So now let's do the OR operation. So OR operation, any one of the operands is 1, we will get an output 1. So first 1, 1, 1, 1. In the last case, both the operands are 0. So we will get a 0. So I don't know exactly what is that, so I'm going to convert that to understand. So that is 4, 1, 1, 1, 1, 0. Which is 30. So the result is 30. So now I'm going to do the shift operation. So I have A equal to 0, 1, 0, 1, 0. So if I do a right shift, which means that this part will move to the right and discarding this value. The output is 0, 0, 1, 0, 1. That is the output of the right shift operation. Figure out the value of 101 in binary. So which is 5. So next what we are doing is we are left shifting 20 3 times. I'm going to copy that 1 0 1 0 0. So I'll be adding 3 zeros here. So again, I don't know what it is. I'm going to copy this and pasting it. So it is 160. 160. So when you use calculator for this exercise, make sure that everything is in D word, because we are using integer here. So integer is 32-bit, so we need D word here. So now what we can do is, let's go ahead and execute this program and check our answers are in line with the program we have written. So first we are going the AND operation, then OR, NOT, right shift and left shift. So corresponding outputs are here as well. So NOT I have not done so far, so we will see that in the calculator later. So currently all the outputs are empty, so I'm going to press F5 again. So we got A equal to 10, B equal to 20, C equal to 0, which is the output of AND operation, D equal to 30, which is the OR operation, E equal to minus 21, which we will discuss later, F equal to 5, which is the right shift, and 160, which is the left shift. So our output is in line with the program. So B is 20. So the binary equivalent of B is 10100. So as this is D word, which is 32-bit, I have to assume that there are 32 minus 5, which is this much. So 1 2 3 4 5. So 32 minus 5, which is 27 zeros are there here, which is not visible, but it is there. So for example, if I NOT that number, I should get 1 for all those zeros. That is what is going to happen if I do a NOT operation. So I'm going to do it. So we got exactly what we were expecting. So we had a 1 here, 0 here, and 1 here and 2 zeros here for 20. And we complemented it and we got this big number. So what is the value of that in decimals? So that is minus 21. So how that got minus? So basically the calculator as well as the program we have written is using a format called 2's complement, which we will discuss later. This big binary number is interpreted as minus 21 using a format called 2's complement, and that is exactly the value of E, minus 21. So now let's go back to our slides. So we have seen these operations. One way or the other, all the tasks done by a computer, addition, subtraction, watching a movie, you name it, everything is implemented at the end of the day by one of the operations we have seen so far. So those are the fundamental operations which a computer can do. Now we're gonna see a program which uses one of the operations we have seen. So what this program does is it has a function called show binary digits. If I pass a value into that function, it will show the binary equivalent of that particular number. So that is the program. The program is pretty simple. It uses shift and operation. So the working of the program is very simple. We have a 1 which is shifted n times to the left. Then we are ANDing that 1 which is at the nth bit to the input number. So due to the property of AND operation, we will get the value of nth bit in this variable. So we are just checking if it is 0 here. If it is 0, we are printing 0. If it is 1, we are printing 1. So we have one example 10 here. So I'm going to execute it to see the output. So we have 1010, which is the binary equivalent of 10. Use calc.exe and the debugger if required to understand this program further when you do this. So let's go back to the slides. So we have seen this demo. Now hexadecimal numbers. So hexadecimal numbers are 16 based numerals. So we have seen 10 based numerals, which are the ones we use in the daily life, and we have seen 2 based numerals which contain ones and zeros. So hexadecimal numbers are 16 based numerals. So they contain additional digits. For example, a equal to 10, b equal to 11, like that, 15 equal to f. Hexadecimal has no relation with computers, so it's just like 10 base numerals. It is very easy to map hexadecimal number to a binary number. So handling the binary numbers are extremely difficult because they are just ones and zeros and they are huge numbers. So to remember or to make some sense out of them, it is very difficult. In most cases, binary numbers are displayed in hexadecimal instead of ones and zeros. This is just to save space and better readability. To know the relation between binary numbers and hexadecimal, let's do a conversion. So coming back to Notepad and calculator, suppose I have a big hexadecimal number, say 1, 2, 3, 4, A, B, C, D. So this is a big hexadecimal number. So let's see the binary equivalent of this. So it's a huge binary number. It's practically not readable, or we are not able to make any sense out of it. So let's copy this. Control A, Control C, Control V. So we have that number in Notepad. So this is equal to hexadecimal, Control A, Control C, Control V. So this is equal to this in hexadecimal. So we don't care about the decimal equivalent of this. So this is not relevant to this discussion. So now what I'm going to do is I'm going to take each of these digits. So first I'm going to take D. So what is the binary equivalent of D? That is 1101. So that is the one we have here. Now what is a binary equivalent of C? So let's go hexadecimal and press C and binary. So that is 1100. That is exactly this one. So 1100. So if you look at that, all the conversions we can do like this. So the conversion is very easy. So all we have to do is convert each digit into the binary and concatenate that conversion. So in this case, so this is the first digit, second digit, which is 2, this is 3, this should be 4, this should be A or 10 for that matter in decimal, B, C and D. So hexadecimal and binary digit has this particular relation, and that is the reason why we use hexadecimal at some places. 10 base numerals and binary digits doesn't have this relation. This type of conversion is not possible in the case of 10 base numerals and binary digits. So now let's go back to the slides. So we have seen this. So now we will discuss shortly about 2's complement. So 2's complement is a method to represent negative numbers in binary. So there is no way to represent a negative number in binary. So what we use is we reserve a bit for the sign of the number. The most commonly used format, we call it 2's complement. So for example, if we go to calc, so I'm going to select a byte here just for better readability. So for example, I have a number 17 up here. So the binary equivalent of 17 is this particular number. Control A, Control C, Control V equal to 17. Now what is the binary equivalent of minus 17 in 2's complement format? So this calc application uses 2's complement, so I can go and do it directly. So decimal minus 17. So now if I go here, I can see the equivalent of minus 17. So this is called 2's complement format of minus 17. So 2's complement is a way of representing negative numbers in binary digits. So this brings to our discussion to our last topic called bit fields in C. Let's straight away go to a program and see what are bit fields. So we have a program up here. We have a struct keyword here. Please note that. So when you represent bit fields, struct is mandatory. And we have 3 members inside that struct. If you have noticed one thing, there is a colon up here and there is a number up here, 2, 7. So basically what this number denotes is that A is not interpreted as a pure integer, but it is a 1-bit number. So A is a 1-bit number. Like that, B is a 2-bit number. So C is a 7-bit number. So what that means? Which means that so A can hold only either 0 or 1. B can hold only 0, 1, 2 or 3. So this is how we use it. Just like using structures, there is no different format there, but we cannot assign numbers like 200 to A anymore, because that will create overflow and the 200 will become either 0 or 1. So again the same thing with B. So it can hold only this 4 numbers. So this is called bit field in C. So I'm going to start debugging this. So for example, I'm going to assign 200 to A. So F10, F10, F10. So A equal to 0, B equal to 3, C equal to 0. I just did an overflow for C. So let me make it 127. 127. And let me make this 3. And let me make this 1. So I'm going to restart the debugger. Now A contains 1, B contains 3, and C contains 127. So those are the maximum values it can hold. If I make A equal to 2, A gonna be 0. So I'm restarting the debugger again. So now A became 0. A can hold only 0 or 1, because A is a 1-bit number. So that explains bit fields in C. Coming back to our slides. So this is the format we do. We need the struct keyword. So we have seen the bit fields demo. And that's all. Thank you very much.